Today, an intuitive derivation of the binomial theorem, which will bring us one step closer to solving the Basel problem. So we'll begin by way of review. What we have here is a binomial x plus y squared, which I've expanded out here to show it that it's x plus y times x plus y. And as you may know, what we need to do is we need to distribute, is the fancy term, each term in the first binomial with each term with the second binomial. Basically, everything on the left gets to shake hands or dance with everybody on the right. So here we go. The x's go together. Okay, and so that gives us an x squared. Okay, and then let's see. Let's send the x over to the y. So plus xy, and now that x is done. Hey, and now we'll do the y. Y times x. We'll write that as x times y. It's all the same. And then y times y plus y squared. And there's always going to be a little bit in the middle here that we can pull together. So we end up with x squared plus 2xy plus y squared. And you might even have that whole bit memorized because it's very simple. Now, what would happen if we wanted to apply that method to something a little bit more out there? Let's check that out. Okay, so now here we've got, there's four of them. We're dealing with a fourth power. So let's see. So we got the x. Okay. Well, we'll do it here. And what do? We distribute it. Okay. I mean, that's really hairy, and we wouldn't really do it that way. I mean, that's what we're supposed to do, but after a couple of these, we start to get all mixed up. So now you may have heard of this connection between these binomial coefficients and this famous Pascal's triangle. There we go. Isn't that beautiful? All right, so let's take a look at this. We'll have a look-see here. Now, for completeness, I'm counting this row here as row 0, and there's x plus y to the power of 0, which of course is just 1. Hey, that's correct. And now we've got x plus y to the power of 1, and so that's, again, this is trivial. We got 1x, 1y, and then here's the one that we just worked out, and it continues along all the way down. So now, again, you may have heard of this Pascal's triangle. I mean, you may have seen it even when you were a kid. You have ones all along the side there, hey? And then as soon as you get to the third row, you need to start doing this. Where this 2, how do we get that 2? It's by adding that 1 and that 1. Okay, so each row generates the row below. So how do we get that 3? It's by adding the 1 and the 2. And how do we get that 6? It's by adding these 2 3s. Okay, so each row generates the row below. And interestingly enough, this gives us these coefficients, okay, the numbers in front of the x cubed, x squared, y, etc. So that's pretty cool. Now, again, we wouldn't necessarily want to do this for like x to the power of 10. And quite honestly, I mean, when are we going to do x to the power of 10? The idea that we of finding a pattern here that we can encapsulate into something that we can get our teeth into is because we want to be able to make statements about all of these numbers going down to infinity, because that's what we need to make broad statements about natural numbers, which is what we need to do with the Basel problem. So let's see if we can find a pattern so that we would be able to say generate you know, the 10th row of this if we were so inclined. Okay, and what we'll do is we'll take another look at this x plus y to the fourth, but in a little bit of a less frenetic manner. Okay, so now I've got it up here, and let's talk about how we get everything. Now, when I did that first thing, and I'm a little traumatized by it, so I'm afraid to do this again. But I'll show you what I'm talking about. We've got x, and we want x to combine with x, and then it combines with another x, and it combines with another x, and so our first term is x to the fourth. And you know what? There's only going to be one x to the fourth because there's only one way to combine four x's. But where we started to get messed up is, well, how about this next term plus something times x to the power of 3 times y? How do we know that there's 4 there? Well, the question that we're asking, I mean, why do we even have x to the power of 3 times y? It's because every time we make a jump, we're going to be combining a total of 4. Okay, and I think that that's fairly apparent. Okay? But sometimes we're going to be mixing and matching. So the question is how many different ways can I choose one of these y's? Okay, say that one, and then leave 3 more x's. Okay, now the way I've said that may ring a bell. I mean, how do I choose, say, one y out of 4 terms? Okay, this is what we talked about earlier, and we derived this binomial coefficient, isn't that? Okay, which is, now you see, this is why these things are called the binomial coefficients. So over here, the question that we're asking is, we've got 4 terms that are combining, and so that's why these exponents are always going to add up to 4 in this case. But the question that we're asking is, for this term that's getting larger, the exponent is getting larger, how many different ways can I pull 2 y's out of these 4 terms? And of course, what we're asking is this. And if you work that out according to the way that we were looking at in a previous video, well, as you may recall, we're going to take that 4 on top, 4 factorial, okay, and then we're going to divide that by 4 minus 2 factorial, and then because order doesn't matter, we need to take the 2 factorial, and you can see that details on that in my previous video. Now again, are we really going to go through this whole process if we wanted x plus y to the 10th? I don't think so. But let's encapsulate this pattern. I mean, what do we have here? So if we've got the nth term, okay, sorry, we've got x plus y to the power of n, okay, our coefficient is going to be, we've got n factorial on top, all right, and then down here, that's going to be, how many y's do we have, and then how many x's are left over, okay? So that's what we need to work out. Let's take a look at this. Okay, I've carried over the x to the fourth along with its solution, all of the coefficients. But now so that we can compare a specific example. So we've got a general x plus y to the power of n. So it's going to go on for n terms. Okay, actually, it's going to go on for n plus 1 terms. We'll have to realize that, because the first term for y is y to the 0. So we don't even put it here, but there's an invisible y to the 0 there. Okay, so we've actually got n plus 1 terms. So the first question for this first, for the first term is, how many different ways can we pick 0 y's out of n binomials? Okay, keeps doing that. And then the next one is, well, how many different ways can we pick 1 y? Oops, not that. 1 y out of n. And then we've got the next one is 2 y's out of n, and it continues on here, so that the number down here, it always matches the y coefficient. Not the y coefficient, the y exponent. And the number up here is always going to be n. And so your final term is going to be n choose n. And of course, that ends up being 1, and that ends up being 1. And really, this is it. This is your binomial theorem. All right. But we're going to put it into a compact form that you can carry around in your wallet and show to your friends. Okay, so we'll do that. Let's make some room. All righty. And so we shall start. Let's put it in red because it's very important. We're summing up a bunch of stuff, aren't we? Let's use the proper symbol. We're summing up a bunch of stuff. Okay, and we're going to start at 0, and we'll use the index term as k. So we're going from k equals 0 to n, which means we're going to have n plus 1 terms because our first term is 0. All right, and what's our general term? Well, what does it look like? It looks like this. It's going to be x and y with some business up here. Okay, so we're going to start with y. I mean, we start with y to the 0, and then it increments 0, 1. We're counting, okay, all the way up to n. All right, so we're going to put the index right here. The y exponent always matches the index. At the 0th term, y is 0. At the first term, y is 1, etc., and so forth. All right. Now, what is the x term going to be? Okay. Well, we want to be careful here, because we don't want to just say n minus 1 like we did up here. We need to make the total of the exponents add up to n. So we'll do this, n minus k. And that's your, we'll put it in parentheses, okay, and that's your x and y with their exponents. As we increment k all the way up to n, we're adding a new term, and then we adjust the exponent accordingly. Now I need to move this over a little bit, because we have a term that we need to add. Not a term, we've got the coefficient. And so what is the coefficient? Well, look at this. we've always got n up here, n. Everybody's n, okay? Because we're choosing out of n binomials. But what goes down here? I mean, we start with 0, we start with 1, we start with 2. I mean, what is this number? It's always matches k, doesn't it? All the way up to n. So we'll do n choose k. And there you have it. This business right here is the binomial theorem, which is all expanded out here. But there it is in a nutshell. We better say what it's equal to. And we've arrived at that by an intuitive understanding of what's going on when we multiply a bunch of stuff. Okay, so in the next video, we will look at the binomial theorem again, but we will prove it more rigorously using a proof by induction. One last thing I want to leave you with is let's go back and look at these binomial, here we go. Isn't that beautiful? Okay, Pascal's triangle. Alrighty, now let's take a look at this. I've written the binomial coefficients underneath each element of Pascal's triangle, because we can represent Pascal's triangle that way. And what I want you to see here is the feature with Pascal's triangle, for example, where you have 3 being the sum of 2 and 1. Okay, so that implies that 3 choose 2 is the sum of 2 choose 1 and 2 choose 2. Okay, and if you recall, check out my video on Pascal's rule, which bears out this relationship. So now we can see why the pattern of Pascal's triangle relates to the pattern of these increasing binomial coefficients. And we'll see you next time when we prove by induction the binomial theorem. Bye.